In this video, we're going to compose a function out of the inverse function. So how do we make a composition out of the two inverse functions? In this case, we have a function x and a function which is f of -1 of x. So these two functions here, f of -1 of x and f of x, we're going to investigate what happens for a certain pair of points or for certain components of the f of x for the independent values for f of x. For a case, we have the t as independent values, and for f -1 of x, we have d for -1 of values. We're going to compare for the results and to compose these functions and what happens by them. So we could define a property about composition of inverse functions. So let's take a look at this particular value here, this particular pair of coordinates here. So our f of 4 is equal to 1.4, as you can see. And in the other side, on the other side here, we take f -1 of 1.4, and f -1 of 1.4 is just equal to 4. So showing you by numerical composition, our f -1 of f of 4 would then be equal to f of -1 of what is our f of 4. Our f of 4 is 1.4, and f of -1 of 1.4 is just equal to, this is equal to 4. So amazingly, they have the same value. When you compose f of 4 inside our f of -1 of x for the value of f of 4, which is 1.4, then we get a similar value which is equal, or which is a similar value when f of -1 of 1.4 is taken. Now let's investigate the opposite. Our f of -1 of 1.4 is equal to 4. So in this case, we're going to get the opposite way, okay? Our f of -1 of 1.4, which is just equal to 4, will be equal to f of 4. And our f of 4 is equal to 1.4, which is, again, amazingly, okay, similarly equal to our f of 4, which is equal to 1.4, taken from these values. So we have a property that is distinct here. If we take our composite function for f of -1 of f of x, then that value of f of -1 of f of x is just equal to, this is just equal to x and x. And on the opposite, on the other way, okay, if we take the composite function f of -1 of x, this is also equal to x. So that's a property common for the composition of inverse functions. Now let's move on to invertibility and the domain of an inverse function. So consider these two tables already presented here. We have again the f of x and the f -1 of x. let us look at the domains. So the domain of this one is equal to 1 to 8. Well, in this case, we have 0.2 going variably up to 3.0, while our range is the domain of the f of negative 1 of x. Our range here is the domain here, and our domain here is the range here, showing perfectly that they are variably that they are inversely related. There's an inverse proportions among the domain and the ranges. They are interchanged, to be exact, or mirrored. The domain of the f of x becomes the range for f of negative 1 of x, and the domain for the f negative 1 of x becomes the range for the f of x. So what is invertibility? Okay, invertibility is a word which means that two functions could be inversely related, and you can get a corresponding inverse function for one function if and only if, number one, they are one-to-one. When you say one-to-one, what is one-to-one again? You have, for any value x, you have a corresponding y value which is unique, meaning that it doesn't appear twice in your graph or in the point system coordinate itself. If you have x2, you have y2, x3, y3, and so on and so forth. Now this is a definition. Okay? A function is invertible, meaning that you can find its inverse function if and only if it's one-to-one. Meaning when it's one-to-one also, it is strictly decreasing or increasing. Strictly increasing or decreasing. What does that mean? When it is strictly increasing or decreasing, it goes something like either this one, okay, or this one, or this one, or this one. Okay, as you can see, this sketch of the graphs of some lines are notably, this is increasing, okay? This is notably increasing. This is also increasing. If we take the full length of a line here, these two are just the same. At the same time, this is strictly decreasing. Okay, so this is the second condition for inverse functions to be, or for functions to be invertible. Now let's examine the graphs. But remember that we took these graphs of our function d is equal to f of t, and our function t is equal to f negative 1 of d, by going over to the scene wherein there is a shift crew bound for 8 hours working on a center stripe, painting it for the duration of 8 hours. In this case, in the first graph, our distance is a function of time, because how long this crew painted depends on the time that has elapsed from 0 to 8 hours, or from a certain time, which is the x-intercept. Okay, actually it's not from 0, but because why is it not from 0? That's the question. Okay, from our, remember our x-intercept is equal to, x is equal to 0.5, meaning the work started at x is equal to 0.5 hours. What happened from 0 to 0.5? Now this is work, and in reality, from 0, from t equals 0 to t is equal to 0.5, if you are one of those crews, first thing that you have to do is to divert the traffic, right? That's the first thing that you have to do. You're going to tell the drivers that, hey, you cannot get into this site because we are doing something, we're repairing, we are painting something. So you have to divert the traffic. Another one is you have to prepare equipment, to prepare the necessary equipment. What are those equipment? The helmets, the construction lines, what else? The blocks, okay? Those are the equipment that we need to prepare. And this take approximately, based on experience and based on previous work, that it takes about 30 minutes to finish this. That's why the crew started at 0.5. T is equal to 0.5 hour. And it ended at 8, the end of the shift. Now on the other line, okay, we could notice that our graph started here. And according to our graph, it started, our y-intercept is equal to 0.5 for the inverse function. But in reality, okay, in reality, time is ticking. Even though, you know, time is ticking, it's ticking. It doesn't stop. So there goes the question in reality whether this inverse function is actually a function. Because taking a look at this point here, okay, we need to include the distance equals to 0 for multiple values of time. Values of time, because notice that our crew has been working on diverting traffic and preparing equipment, but still the distance is 0, and we have time. So we have multiple values of time. In this case, it's x for the original function. We have to simply put it, okay, in picture. We have an x1 for at d is equal to 0. At d is equal to 0. There are multiple times there. So we have multiple values of y. So therefore we have distance equals 0, and we have y1 because clock is ticking. We have another one, 0 at y2. Remember, clock is ticking. And 0, y3 until 0 to 0.5. And this is now the y-intercept when finally time is the y-intercept for time is gotten for the inverse function. But in reality, this thing here, which you see, climbs. It climbs. You cannot answer the question. We cannot answer the question, how long has the crew been working when the distance is 0? It's simply foolish in the real world. Distance is 0 because they are preparing the equipment and diverting traffic. Therefore, the crew did not yet do any type of painting on the center stripe. So that's why the inverse of y, or in this case our d is equal to f of t, and y is equal to f of x in general term, is not a function. It is not a function. Why is it not a function? The definition for function is that it should be one-to-one. Again, I am reminding you that the definition of a function is that it should be one-to-one. Meaning there should be no multiples of y for a certain x value. So as you notice, we have multiples of y here for a certain value of x, which is equal to 0. So this is not a function. This t is equal to f of negative 1 of t is therefore not a function. In other terms, it is a relation. And therefore, this is an inverse relation of our original function, y is equal to f of x, or d is equal to f of t. So now in summary, if our t is equal to 0.5 hour, then our distance is equal to 0 for this case, okay? When our time is 0.5 hour, our distance is still equal to 0. That means that's our x-intercept, and that means that the crew has started working only at the time which is equal to 30 minutes after they have started operating on the painting of the crew stripe, of the center stripe. What else? We still have to include the time from the beginning of the shift. Of course, we still have to include the time because they are being paid for the 8-hour shift. And again, from the time of the beginning of the shift, they have to make some preparations, like diverting the traffic and preparing the necessary equipment. So the crew diverted the traffic and prepared necessary equipment. And note that for f of negative 1 of x, there are multiple values of y when x is equal to 0, as I have told you. If we cannot just answer the question, how long has the crew been working when the distance is 0? What is that question? That's in reality, okay? Looking at the graphs themselves, they seem to present as seemingly comfortable and perfectly in inverted relations, or inverted relationship between each other, but in reality we cannot take them as inverse functions. Notice that f of x is a function, and our f of negative 1 of x, which is the inverse relation, is not a function. Therefore, we can say that a function that is one-to-one or strictly increasing or decreasing, such as our example, is invertible. But in reality, as we see it, the inverse of our original function, d is equal to f of t, is not really invertible. So the definition of invertible should be strictly increasing or strictly decreasing, and should take into consideration the property which is one-to-one. So our function here, although at first it seemed perfectly fit for this requirement, but in the end, our conclusion, taking the reality on our side, it is not invertible. Now, if the function is invertible, for instance, then we could use the notation f of -1 for our inverse function. And lastly, a function is not invertible if we have multiple values of y appearing for one function only, which means it's not one-to-one, which means therefore that is one-to many, and that's not a function based on previous algebraic experience. It's not a function, it's just a relation. So a function f is not invertible if there are multiple values of y. There are many values of y for one value of x only. And for a function, y must be unique. And or rather, x must be unique. So that ends our explanation for invertibility and the domain of an inverse function. Thank you for watching.